Good morning everyone! Hi, I am Aimi and today I'll be walking you through the computer architecture of the AMD Zen 3 Zen processor. Think of this as the blueprint of a high-performance engine designed specifically for mobile workstation and also gaming laptops. My goal is to show you how AMD redesigned this engine to be faster and smarter than ever before. First, let's look at the big picture. Zen uses a system-on-chip SoC design. This means the CPU, GPU, and memory controllers are all living on a single piece of silicon. Why does this matter? It's like moving all the shops in a city into one mall. It reduces time travel, latency, and also saves energy. The big change here is the move to a unified architecture, which allows all the cores to talk to each other faster than the older design. Wait a minute, look at this diagram. On the left is the older Zen 2 design. You can see a clear line splitting the 8 cores into 2 separate groups. Each group only had access to 16 MB of cache. If core 0 wanted to talk to core 7, it was like making a long distance phone call. It was slow and caused latency. Now look at the Zen 3 side on the right, the architecture used in our Zen chip. That middle wall is completely gone. All 8 cores are now in one big room and they all share a massive 32 MB pool of L3 cache. This is the big change I mentioned. By removing that physical and logical barrier, AMD allowed data to move across the chip almost instantly. This is the secret to why this processor handles multitasking so much better than the generations before it. Now, let's look at the 8 cores powerhouse. These cores are built on a tiny 7nm process which is incredibly efficient. Thanks to simultaneous multi-threading SMT, the chip handles 16 logical threads. Just imagine, each chef with 2 hands each. If one hand is waiting for a pot to boil, the other hand is chopping vegetables. This keeps the processor busy and eliminates what we call pipeline bubbles or wasted times. The front end is the branch traffic controller. It features a faster branch predictor that guesses what the software will do next. Because it is so accurate, it has no babel capacity, meaning it can reuse predicted instruction in the very next cycle without any gaps. We also have an OP cache that stores already decoded instruction, allowing the CPU to skip a step and save power. If we look at the specific block diagram of the Zen 3 front end, we can see exactly why it is so much faster than the older designs. Notice the branch predictor at the top. This is the unit that allows the CPU to have no bubble capacity. By having a massive branch target buffer, it predicts where the program is going so the execution cores never have to wait. Also, look at the OP cache. This is basically a shortcut. Instead of the CPU having to decode instruction over and over, which wastes time and battery, it saves the already decoded instruction here. So, the next time that task comes up, the CPU just grab it and goes. Moving on, so as we already know, all the chips had their L3 cache split into separate pools, while Zen 3 uses unified 16 MB L3 cache. Now, every core can access the same big bucket of data instantly. To make it even faster, we have shadow tags, which act like a cheat sheet, so we can see what's in each other's local memory without wasting time asking the main RAM. I want to pause here because the L3 cache redesign is the hero of the Zen 3 architecture. To explain why this is a breakthrough, let's use a library analogy. In older design, the CPU's internal library was split in half by a locked door. If a core was sitting on the left side, it couldn't reach the books on the right side. As you can see in this architecture diagram, Zen 3 removed that door entirely. We now have a unified 16 MB L3 cache. This is one giant bucket of high-speed data that all 8 cores can reach into at the exact same time. But how do they stay organized? That's where shadow tags come in. Think of shadow tags as a high-speed catalog system. Instead of a core wasting time searching the whole library, it checks the shadow tags to see if a neighboring core already has the data it needs. By moving to this shared library model, AMD virtually eliminated the long-distance travel data used to have to do, which is the #1 reason for the massive jump in the performance we see in the Ryzen 9 5900X. Now, how fast can it go? The Ryzen 9 5900X has actually base speed of 3.3 and can go up to 4.6 Hz. But speed is nothing with that timing. We have 3 internal clocks, MCLK, UCLK, and also FCLK. For the best performance, this must run in a 1:1 ratio. Think of it like 3-man rowing team. They are most powerful when they pull their oars at exactly the same time. Alright, to move all that data, Zen uses Infinity Fabric. Because this is a monolithic SoC, the highway stays on one chip. This avoids traffic jams that happen when data has to jump between different chips. It's paired with dual-channel DDR4 3200 memory, providing a direct, high-speed connection between the CPU and GPU for smooth gaming and also video editing. Alright, laptops need to stay cool and save battery, so we use DVFS technology to adjust voltage and speed every second based on what you are doing. If you are reading an email, core capping turns off and use cores to save energy. If you start the game, precision boost overdrive kicks in, checking smart sensor for heat level to push the speed as high and safely as possible. Alright, to conclude, the Zen 3 Zen is a master of balance. It isn't just a minor update, it is a thoughtful redesign. By unifying the cache and optimizing how instructions move, AMD created a chip that is more responsive, more powerful, and also more efficient. It sets a strong foundation for the future of mobile computing. Alright, that's all from me. Hope you like this video. Bye!